Here the question is, when a block of mass m is suspended by a long wire of length L, the S is a capital L, the length of the wire becomes capital L plus small l. That means the small l represents the extended part of the wire. The elastic potential energy stored in the extended wire is. So this is a problem we are going to solve now.
Here L represents the wire length. After adding the weight of mass M, the wire got extended the length small l. Now the total length of the wire, it will be equal to L plus L small l. So after adding the mass, the wire got stretched up to small length L. Here at this point the energy has been stored because the wire is elastic. After removing that wire, the wire will retain its original length. So what is the stored potential energy, they are asking? What is the stored potential energy? One can derive from the Hooke's law. Even you can apply the Hooke's law, that is equal to minus kx. Then what has been the work done for the elongation of the wire, one can calculate. From there one can calculate what is the stored elastic potential energy. That would be equal to half time the stress time, the strain time, the volume of the wire. This is the stored elastic potential energy at the end of the wire. So here stress represent, you can write the simple definition. The stress is the force per unit area. That is in general the definition of the stress. Its unit is Newton per meter square. Here where is the area, you can look at here. But here wire, if you are just to zoom the wire, it has the cylindrical shape, then it has the area at the bottom as well as the upper. This is looking like, if you are zooming the wire, it will be looking like that. This is the area. We are here we are attaching the block of mass m, then there is a force acting on that area. So you can define the stress is equal to, the force is mg. Here it is acting on the wire, the mass of the block times the acceleration due to gravity. The area in general, you can represent the top area or bottom area. If you are assuming this area, it's a uniform cross section area, that is a A. The strain is, you can, the general definition for the strain is the change in length divided by the original length. Change in length divided by the original length. So here the change in length is the small l, that is a change in length. The original length of the wire is capital L. Now we want to know what is the volume. If the wire is, it's, if you are assuming this looking like a cylinder, the cylindrical volume is nothing but the length of the cylinder times the area of the cross section. So here the wire volume, the wire is in the form of cylinder, so you can represent the length of the wire times the area of the cross section. It will give the volume of the wire. So now we know the stress, we know the strain, we know the volume. We can substitute here. Then the stored elastic potential energy, that would be equal to half time the stress is the force per unit area, the strain is the change in length by original length, the volume is in general it's not small l because it's a volume, it should be the capital L, the total volume, capital L times the area. Even though if it is extended, the area of cross section will decrease, but the total volume remains constant. So in general you can calculate the volume before adding the load. That volume is equal to L times A. The volume remains same because the number of particles we are not going to lost. So even though the area of cross section after load applied, the area of cross section will change, the length also will change, but the product will be same, the volume. So the volume is capital L times the area of the cross section. So the elastic potential energy, that would be equal to, you can cancel this L, A area of cross section, so half time the force into the small l. So half time the force is nothing but the mass time the acceleration due to gravity into the small n. So this much amount of energy has been stored at the bottom of the wire. Once if we are releasing this energy have to convert it into kinetic energy, then the wire can attain the original length, the capital L, after removing this. So this form of potential energy can be converted into kinetic energy once if you are removing the load from the bottom.
So from the explicit analysis of the problem, we got the answer that is equal to 1 by 2 mg small l. This is the third one is the right answer.